insediamo. Buongiorno, allora ci siamo.
Good afternoon. Welcome to this meeting which looks at the state of emergency of the human person, the need to return man to his original self. And we wanted to ask the scientific world through a theme which is, of course, central to scientific research, but which also picks up something very profound about human experience, the dramatic existence of human life and the search for a meaning. And therefore, we developed the idea of putting time at the center of our debate. I think it was a courageous choice because it's one of the most profound and yet fleeting and difficult to grasp ideas and of a comprehension of our reality. The nature of time in science and in human experience is the title of the meeting. And in fact, scientific inquiry is accompanied by this reality of time in very many ways, in a profound way, but also in a silent way, I'd say. It doesn't necessarily appear as the first issue to be looked at. It's perhaps difficult to note, but every scientific piece of scientific inquiry uses, in a profound and pervasive way, I think, the very notion of time, both at the experimental and also at the theoretical level. We are talking about time in physics, especially today. And here we can see that the great physical theories are in fact acknowledged depending on the type or the way that they use time. Quantum time, classical time, and so on. The whole theme of time underpins profound questions in the scientific world, therefore. For example, the theme of evolution, the span of time that nature has taken, or the concept of causality, determinism or non-determinism. Here we see that the themes come from science, but they then go on to link in to wider spaces of reason from philosophy and also theology. And in fact, time, as well as being a physical variable, which is looked at and used in science, is a profoundly and mysteriously a reality which everyone experiences. Think, for example, of the idea of memory, remembrance, memory of the past, expectation of the future, attention to the present time, which is, of course, something that St. Augustine looked at. St. Augustine, in fact, recalls, as John Waters did yesterday, and they didn't agree, by the way, he cited this comment of St. Augustine, "What therefore is time?" he said. "If nobody asks me, I know. If I want to explain it to somebody who asks me, I do not." And that's interesting. Our friend Andrea Moro, a linguist, says that from a linguistic point of time, from a linguistic point of view, time, he said in a book, is codified in human culture in a sophisticated way, so much so that in fact nobody has been able to elaborate a theory that has been able to describe what grammatical time is. Even in our spoken word, there is something mysterious linked to the question of time. So you can see that there are many disciplines that in fact include the question of time. And today's meeting is, if you like, a preview of a congress which we're going to hold in San Marino, organized by Eurosys for the 7th time, together with the meeting of Rimini and the University of Rimini. And we have invited about a dozen odd scholars of different disciplines, including our two great guests of today to look at this theme, the nature of time in science and human experience. Now, I'd like to mention these people who are going to be present at this Congress. Most of them are here today, and two will take the floor today. They cover different disciplines from biology, quantum mechanics and physics, psychology, philosophy, theology, and so on, to mention but a few. Giorgio Bucciolati, many of you know him. Mark Buena, let's have an applause at the end. Mark Buena, Paul Davies, George Ellis, Constantino Esposito, is José Ignacio Latorre, John Lynch, Hans Maynard, and Gaz Obermann. We'd like to thank them all because it will be a dialogue that the meeting makes possible, looking at a theme with the idea of learning one from the other. I can assure you that's no common occurrence. Now I'd like to give the floor and present our guests, Paul Davies and José Ignacio Latorre. We'd like to thank them very much for coming here. I'm not sure which of the two of them has traveled longest flight to get here, because one comes from Australia and the other comes from Singapore, and they had to wedge in their other appointments to be here today. So thank you. Now, Paul Davies, we all know him. He is a very famous world figure. And we all know him because he has already been here twice to the meeting. He is concerned with theoretical physics, cosmology, and astrobiology. He is at the Arizona State University, and he is author of Beyond. He is the head of Beyond, a Beyond Center for Fundamental Concepts in Science. And he is the leader of the Center for the Convergence of Physical Sciences and the Biology of Cancer. In recent years, he has opened up to this new frontier. He has worked at the University of Cambridge, London, Newcastle upon Tyne, and then he went to Australia, to Adelaide, to Macquarie University, where he developed the Australian Centre of Astrobiology in Sydney. He has won numerous prizes, very important awards. I'd just like to cite a couple. In '95, he won the Templeton Prize, one of the most prestigious awards, cultural awards in the world. He also has won the Robertson Cosmology Prize. In 2011, he's also a member of the Order of Australia. In fact, he had an asteroid dedicated to him in 1992, which is called, of course, Paul Davies asteroid. And so I think this is the recognition of the work that he has done on the impacts of asteroids. He is well known for being the author of several bestsellers on science in a profound manner, accessible to everybody, but scientifically very profound. And his last work is A Strange Silence. Are We Alone in the Universe? This has recently been translated, by the way, also in Italian. He's also famous as a TV and radio commentator throughout the world. So thank you really for coming. José Ignacio Latorre is a theoretical physicist from Spain. He is full professor of theoretical physics at the University of Barcelona, and he is an authority, a world authority on quantum physics, quantum information, in other words. And we're going to have an example of this when he talks about time and also the physics of other energies. He got his PhD in Barcelona. After that, he went to the US, to MIT, and he worked at the Mitsborn Institute in Denmark then. He also directs the Benasque Center for Science, where there are very top-level meetings which take place and have taken place for some years in various disciplines. Again, his is an interdisciplinary approach. and which goes from the string therapy right through to the software of Android therapy. And he is also a commentator and he has, in fact, founded a radio-television channel via web, and he has curated 2 exhibitions on the relationship between physics and aesthetics. And he is also an expert in the transferring of basic information for businesses and economic endeavors. For example, on the forecast of stock market or cell telephones and so on. Now, the last thing I'd like to say with regard to Ignacio is that, well, being a great physicist, he's a connoisseur of wines. He produces wines, and he has developed a winery with his colleague, and on the label of the wine you have Feynman's diagrams that he has put on the label. And he was telling me just a while back that, can I say this? Asked the chairman. Before the discovery of the Higgs boson that we talked about last year, there was a label of his wine that already indicated Higgs boson's diagram. So I don't know whether that's a scientific publication or not, or it can be held as a scientific publication or not. But anyway, it is a fact. It's on a bottle of wine. Now, to start, we have asked each of our authors in about 20 minutes to tell us something about how time plays a role in the sort of research that they investigate. Let's start with Paul Davies. One of the things that we usually take for granted is the direction of time. I mean, the fact that time flows in a certain direction, the so-called arrow of time. This is a theme that Paul has looked into and he will talk to us about.
And ladies and gentlemen, let me see if I can operate this. Okay. No. On May the 20th last year, there was an earthquake quite close to here. And this is a picture of the earthquake. And this sort of damage is very familiar to Italians. One way of describing what has happened here is that the clock tower has gone from a state of order to a state of disorder. And this was caused by the earth shaking. Imagine if you were to go to this place now and stand in the street, and the earth begins to shake, and you see the bricks rise up and make a new clock tower. That would seem to you like a miracle. This is an example of what scientists call the arrow of time. That there are processes that go in one direction in time, but we don't see them go in the other direction. This is very familiar to us. Imagine that you take a movie film of any everyday scene, and then you play it backwards to an audience. The audience will always laugh when they see it. And the reason they laugh is because they know they are being tricked. What they see looks impossible. And so we have this arrow of time that gives a distinction between past and future. And in daily life, we are never in doubt about that direction. We never confuse past and future. How can we study this scientifically? About 150 years ago, physicists began to formulate a general law of nature that describes this one-way in time process. This law is called the Second Law of Thermodynamics. And in its original form, it stated rather simply that when there's a hot object and a cold object, the net flow of heat is from the hot object to the cold object. If you put a snowman in front of a fire, you would expect to see the snowman melt from the heat of the fire. You wouldn't expect to see more snow form and the fire get hotter. So the flow of heat is from left to right and not right to left. That asymmetry is the same as the arrow of time that I've been mentioning. We see this second law of thermodynamics at work not just on Earth, but in the entire universe. Some years ago, I took the trouble to compute the fuel bill for the sun. If the sun had to pay, or if we had to pay for the energy that the sun uses, how much would it cost? And that number there is how much it would cost every second. That's the amount of heat that the sun is pouring out into the universe every second, never to return. And what is true of the sun is true of all of the stars in the universe. They're all busy churning out heat and light and spreading it out into the universe, into the dark, cold parts of the universe. And it doesn't come back again. Every star, including the sun, must have a source of energy to provide for this heat. And so long as the energy lasts, the flow of heat will continue. But because every star has a finite stock of fuel, stars cannot go on shining forever. Our sun is about halfway through its life cycle. It's about 5 billion years old, and it has a few more billion years to go, after which it will run out of fuel. And then our sun will start to die. All stars die eventually, and the next picture shows the death of a star. This is an example of a star that died suddenly in a gigantic explosion called a supernova. And the picture shows a galaxy with the bright spot beneath it as the supernova. That single star, for a short time, shines almost as brightly as the whole galaxy. And then what is left of the star might be a black hole. It will cease to shine. And what is true of that one star is true of all stars. Not all of them will blow up like this, but they all live for a finite time. So, over a century ago, physicists came to realize that because of the second law of thermodynamics, the entire universe was on a sort of one-way slide towards a final state of thermodynamic equilibrium, a state of maximum entropy or maximum disorder, which they called the heat death of the universe. The person who first articulated this gloomy prediction was Lord Kelvin, who in 1852 proclaimed that the universe is in fact dying. a very depressing prospect. This is an example of the arrow of time on a cosmic scale. And it tells us that if the universe is moving towards a final state, a final heat death, then it must have started in a very different state. And I want to illustrate this by showing a simple experiment with a box of gas. Imagine we have a box, and on the left-hand side is the yellow gas, and on the right-hand side is the blue gas, with the molecules rushing around chaotically. And then we take the partition away. What happens next? The molecules mix together, they intermingle until they're spread throughout the box with no distinction between the red and blue molecules. This is a good example of an ordered state making a transition to a disordered state. The top state is more ordered than the bottom state. We would not expect to look at a box of gas like this and suddenly see that transition happening. We would not expect to find the two different gases unmixing. So we have here an arrow of time of going from an ordered unmixed state to a disordered mixed state. And we don't expect to see the reverse. But this is very strange, because the laws of physics that dictate how molecules move and interact with each other are completely symmetric in time. This led in the 19th century to a paradox, sometimes called the reversibility paradox, that the collision between any two molecules is completely symmetric in time. If the molecules bounce off like that, then you can run it backwards and they bounce off like that. And they would go back to their original state. So what that suggests in a box of gas is that there is no intrinsic arrow of time. That the reason that we see an arrow is because the state of gas in the box starts out ordered. So we understand the arrow of time when it comes to boxes of gas in terms of preparation of an ordered initial state. What can we then say about the origin of the universe? We think the universe began with a Big Bang 13.8 billion years ago. Marco just told me the latest date today. And we would expect that the universe would start out in an ordered state. It's possible to get a glimpse of what the early universe was like from the very project on which Professor Bersanelli works, which is the Planck mission of the European Space Agency. And here he is, in charge of this important project. And what you see there is a heat map of the sky. And what really interests cosmologists like Marco and myself are the little variations in heat across the sky. But today, for my story, it is more important that we concentrate on another fact, which is that the heat radiation across the sky is very uniform. To within 1 part in 100,000, the temperature is the same everywhere in the universe. And that tells us that when the universe began, matter was distributed very smoothly. If we look at the universe today, we see something very different. We see matter aggregated into stars and galaxies and clusters of galaxies. The matter has clustered together. And the reason for this is gravitation. Gravitation has the power to pull matter together into clumps. And over time, these clumps of matter get bigger and pull more strongly. The ultimate end process might be a black hole. In cosmology, this is the most important arrow of time. The transition from a smooth early universe to an increasingly clumpy later universe. And the other processes, such as the emission of sunlight, follow from that fundamental process. So an explanation of the arrow of time requires scientists to answer the question, why did the universe start out so smooth? Why did the Big Bang create a smooth universe? We don't know the answer, but a popular idea is called inflation. It says that just after the Big Bang, the universe jumped in size by an enormous factor. So any earlier irregularities would have been enormously stretched and smoothed out. Whilst this must be part of the truth, it still leaves unanswered the question about the ultimate source of the arrow of time, because we want to know why the universe was born in a Big Bang in a physical state that was able to undergo inflation. This question remains unanswered. And so I'm going to finish my presentation by giving you one possible idea about how we can recover an arrow of time in a universe governed by time-symmetric laws. And that is the idea that perhaps what we have been calling the universe is really not everything there is. Instead, perhaps it is a small, perhaps an infinitesimal part of a much larger system in which there is not just one Big Bang, but many bangs scattered throughout space and time. And we call this the multiverse. Many universes. This is very speculative, but if it is true, it offers a solution to the puzzle of the arrow of time, because each universe may have its own arrow of time, but they can point in different directions. So when you stand back and look at the total picture, there is no preferred direction of time. But each individual universe would have a birth, an unfolding of history, and a death, a life cycle just like human beings. But overall, the system is eternal and has no arrow. If there were no arrow of time, human beings could not exist, there could be no life. So if there are universes in this mixture, like the one that has the arrow pointing both ways, then in those universes with no clear arrow, there could be no observers. So perhaps it is no surprise that we find ourselves living in a universe that has a definite past and future. And whilst what I'm saying may be very far from the correct explanation, it illustrates to you some of the deep puzzles that pervade all of physics and have led many great physicists over the years to wonder how we can explain a world that has certain features which are not contained in the underlying laws. And that is a deep challenge for science, not just with the arrow of time, but with many scientific puzzles, including, of course, the existence of human beings and observations and the existence of consciousness. So on that philosophical note, I will finish my presentation. Thank you.
Grazie, Paul.
Thank you, Paul. Now let's go to, or from the macrocosmos to the microcosm. And we're going to ask José Ignacio to take us to an understanding of time in quantum science, physics. And I think here too we'll find surprises.
Sono veramente contento di essere qui.
I'm very, very happy to be here. I'm sorry that I can't speak Italian.
So, you see, how are you today? I don't carry a watch. So, what time is it? What you are seeing here is what we call the universal time coordinated in the Earth. So there are atomic clocks distributed in different layers that are called a stratum, that they control what we call the time of the Earth. So this time of the Earth is precise to 1 part in 10 to the 9, in 1 part in a billion. This is amazing. I mean, humans now, we have an amazing control of time. And this control of time is due to the fact that we control the physics at the quantum level. We are using quantum clocks to define our time. Okay? So let me now start my presentation. Starting with a picture of a painting by Davies. I discovered that Davies in 1954 painted this soft clock at the time of the first explosion, where he learned a little bit about quantum mechanics, about the Big Bang, and he produced this fantastic painting. I put this picture because I want to always remember that all of us come from very different backgrounds and we all have different experiences for time. You see, there might be psychologists, there might be people devoted to economy, to law. All of us have a different understanding of time. Okay? And I don't think I can give you more information but the one that comes from science, because this is what I'm studying myself. So my talk will only be about the concept of time in physics, in particular at the subatomic level. Okay? So let's go for it. I will try to give you 3 ideas. The first idea is about precision. We have a lot of control on the precision of time. The second idea is what is time in our equations. And the third and more subtle and delicate point is whether the laws of physics control the evolution in time in such a way that everything is determined or not. So let's go for the first. Precision. You see, you can buy nowadays an atomic clock for less than $100. So you can go and order in Amazon.com, you can buy an atomic clock. This little atomic clock has a precision, as I said, of 1 part in a billion. But it was not like that in the old times. What is a clock, really? What really is a clock? Okay? So you see on the left, you have a pendulum clock. In the center, you do have a solar clock. And right, we have a mechanical clock. You know what they have in common, all these clocks? What is it, a clock? What really is a clock? Well, you see, a clock is a physical phenomenon that provides a reference cycle. That's it. So if you have a pendulum, you see, this is a periodic phenomenon. If you have the solar clock, you have the Earth spinning, which is a periodic phenomenon. If you have a mechanical clock, you will have springs and wheels that define a periodic phenomenon. So a clock is just engineering a periodic phenomenon in our advantage, so that it is robust, which is precise, which is reproducible, which is small, which is not expensive. But this is, in a way, it's a clock. It's simply controlling a periodic motion. So what is the definition of second that we have nowadays? Well, it's a periodic motion, but it has to do with a property of light, of photons. It's what we call the frequency of one particular photon, the one that is emitted in cesium. So we define a second as it is written here, 9,162 million, or whatever, cycles per second. So this is the definition that nowadays we have for time, for the second. But our technology is so much advanced that this technology is nowadays obsolete. So there is a debate nowadays on how we should change this definition for one which is much more precise. So let me be simpler. Let's make an ideal clock. So look, this clock is very simple. There are two mirrors, and one photon will bounce back and forth from the two mirrors. Every time the photon hits a mirror, it's a click. So you will see it will be click, 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 click. So this is my clock. It's an ideal clock. So you see it's click, 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 like that, okay? This is my clock. Okay? Now, what happened if I move my clock? So please, you have two clocks. One is on top. Okay? And this clock is clicking. Click, 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 click. Okay? The top clock. But the second clock is moving towards the right. But the photon always travels at the same speed. It's moving at the speed of light, which is constant. Now you see the trajectory of this second clock. You see, it's taking more time to hit. So while the first clock makes click, 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 the second clock is slower. It will be doing click, click, click. So you see, the clock which is at rest thinks that the clocks, he sees the clock in motion slower. So you see, this is the idea. It's so simple like that. It's the idea that the measurement of time depends on the state of motion of the clock. And this is the core of relativity. So if we are at rest and we see another clock moving, we see that this clock is slower. Okay, let me now show that with motion. So this is the same thing as I said before. You will have the left clock clicking at rest, and the other one will be moving at the right, and you will be seeing a slower click. So could we have it? Look at the time. The first does click now, click on the second. So you see the second clock is slower. So you see, this is not theory, this is reality. Okay? So we go ahead, and you see, this is a fact that it's a very small change, unless the speed is very large. But you know, this is exactly what we need nowadays to have GPS. So I want you to remember every time you go on your car that you are getting the data from satellites orbiting the Earth, which have atomic clocks with a precision of 1 part in a billion, and that you are making corrections that the clocks are slower and faster due to the effects of relativity. So you see, what was pure science, basic science, in the early 20th century is our present technology. It's the way we make business nowadays. It's something that we cannot live without it. What is the precision frontier of time nowadays? Well, look, this is a plot of how precise are clocks along the history. I voluntarily stop at 2000. So you see, it's a precision of 0.1 nanoseconds per day. Well, as of April of 2013, so this last April, the best clock that humans have made has a precision of 1.6 times 10 to the minus 18. The day that these clocks will be commercial, they could provide a precision in positioning in this room, which would be better than 1 micron. So it's not unbelievable that in the future, surgery on humans would be made by machines which are controlled by clocks, which are optical clocks. Okay? So I invite you to think what would be the future with a positioning of 1 micron. It would be unbelievable the kind of things we will be able to do. Yeah. So with quantum mechanics, we are mastering time. So my second point was the concept of time. What is time in an equation? Well, look, we have a set of particles on the left. They have forces, they move. And after a while, they are in a different position. So we want to see the measure of how the positions change while I have my clock, which is doing click, 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 click. So I want to see a motion as referred to another motion. So we will say these particles have changed position that much when my reference phenomenon changed that much. So this is a very simple example. A particle is moving at constant velocity. On top, I have my clock doing click, click, click. And now I check where the particle is every time I have a click in my clock. And I see the particle moving, click, click, click. So again, I do click, click, click. And I see that every click, it moves the same quantity of distance. So that's velocity, the same displacement in the same click. That's it. So I want to know where the particle will be in a lot of clicks. So I simply do velocity times the number of clicks. So time is simply a parameter relating our motion to another reference motion. If we put forces, the velocities would change. But the idea is the same. We want to see the change of motion as referred to a reference motion. So in classical physics, time is a parameter. We don't measure time. Okay. We count how many clicks another thing does. It relates a motion to another motion. So if our reference motion is perturbed, all the measures of time changes. And moreover, it sets causality. It produces the fact that if there is a cause, there will be an effect. Well, in quantum mechanics, nothing changes. Time is a parameter. It relates the evolution of the quantum system to a classical clock. And it sets causality. Again, we don't measure time. Time is not unobservable. And I go to my third time. So I hope Marco allows me to provoke you. Okay. Of course. You go home with something to think. Well, I'm trying to understand time, and I see that the forces provoke a motion and I simply can write an equation that tells me what will be the future state of that system. So I see that there is a relation between the causes and the effects. Let me go a little bit deeper on that, okay? Because you see, it is there, whether we are free, whether there is justice, makes sense, what is our fate. So the very basic questions which are in our heart, okay? So the first person that wrote in a clear way the concept that it may happen that the laws of physics set the future was Marquis Pierre-Simon Laplace. He wrote it in 1820. I will try to make it's written in the original French. There are some mistakes, but essentially it says the following. If an intelligence could have all the data of the positions and velocities at a given instant in the universe, and that intelligence would know the laws that control these particles, that intelligence could compute any future state of the universe. He says, to that intelligence, to past and future are present. Okay, this is a famous statement by Laplace about whether the future of the universe is determined or not. But we humans are very often think that this is impossible. Because we look at nature and says, it's impossible. But this is not quite correct. I mean, complexity is about that there are many particles and might be very difficult to predict. But it doesn't say that this is not predictable. It may be very difficult to understand the initial conditions of a system. But again, this is not saying that it will not be deterministic. We may not have enough computational power. Or we may not even know the laws of nature. But the issue is whether there are laws which are maybe not known to humans, which sets in a rigorous way the relation cause-effect in nature. Well, it turns out that when you go to quantum mechanics, a surprise is there. It turns out that in quantum mechanics, it is not true that what we will see is fully determined by the state and the laws of physics. It turns out that in quantum mechanics, the evolution of the system is deterministic, but the measurement is it's probabilistic. So quantum mechanics postulates that there is an inherent randomness in the process of measurement. So you see, this is extremely subtle, very subtle. Okay, so let me start to summarize. Quantum mechanics postulates randomness. so does not follow determinism, but does not violate causality. Yet, probability's randomness has nothing to do with will. So the debate on free will is simply identical. We have not made any progress on that. Moreover, it may well happen that quantum mechanics is not the final theory. Very likely, we will learn more, and at some point a new law will come. So I finish with a summary. I try to say three things. First thing, believe me, quantum mechanics is amazing. It has produced the best tools humans have ever made. We have NMR, we have laser, we have circuits, we have clocks, we have nanotechnology. From the conceptual point of view, time is not unobservable. It's a relation between two phenomena. But causality is obeyed by all the laws of physics. And the third point is that quantum mechanics introduces randomness, but no will. So we can debate about determinism, and we can debate of a more profound subject, which is our human experience on time. In a way, all are the difficult questions, the ones which I am not addressing, simply because I don't know. Okay, I simply don't know. So, thank you very much.
Grazie.
Thank you. We have time now for a couple of questions. Let's continue this dialogue, and I would like to ask one specific thing of Paul, and then to José Ignacio. To Paul, I'd like to ask this. One of the most intriguing results of contemporary science that comes from cosmology is that which indicates that time itself would seem to have had a beginning. And we tell a story when we're talking about the universe, a story that has a precise moment in time in the past that we can determine today with a considerable degree of precision. I'd like to ask you, Paul, how do you perceive and see the situation of time that seems to have had a beginning, perhaps just the beginning of our own universe, of our local universe, if you want to put it that way? And were we to find out that some of these speculations that are fashionable today were feasible, or that we could get to a cosmological time without a beginning at the of time in the past, would it be more intuitive? I mean, is it not less mysterious, a time that doesn't have a beginning or a time that has a beginning? Can you talk to us about that?
It's equally puzzling whether time has a beginning or does not have a beginning. The first important point to communicate is that 200 years ago, people perceived time and they perceived space. But they thought they were just there. They were the arena in which the great drama of nature is acted out. After Einstein, we now understand that space and time are part of the physical universe, and they can change, they can even be manipulated by human beings. And so the idea that time and space just being there is no longer tenable. And that opens the possibility for both time and space to come into existence or to go out of existence. When people talk about the Big Bang, in a simple picture, it is the beginning of time. That solves some problems. For example, the question, what happened before the Big Bang or what caused the Big Bang, are simply meaningless because there was no time before the Big Bang. Stephen Hawking once expressed this by saying, asking what happened before the Big Bang is like asking what lies north of the North Pole. So the answer is nothing lies north of the North Pole, not because there is some mysterious land of nothing there, but because there is no such place as north of the North Pole. In the same way, there is no such time as before the Big Bang. That still seems very strange, but it's not new, because St. Augustine said in the 5th century, the world was made with time and not in time. So this is a very old idea. But it still leaves us feeling dissatisfied because although we cannot talk about a cause for the Big Bang, we can still ask, why did such a thing happen? How is it possible? Perhaps quantum physics provides the answer to that. But the subject of quantum cosmology is still in its infancy. However, this subject does also provide the possibility, which I mentioned in my talk, that there may be many bangs scattered throughout an eternal space and time. And in that picture, what we call the Big Bang in our universe was not the ultimate origin of all physical things, but just the beginning of our particular phase of the universe in this particular region. Let me just finish by saying that if there were no beginning to time, that still leaves us with problems. You don't explain the existence of something just by saying it has always been there. So we are still left with an origin mystery, whether this origin is at a finite moment in the past or pushed back to minus infinity. We still have a problem.
Del resto io non sono un esperto, ma mi risulta che San Tommaso d'Aquino
I'm not an expert, but I think that St. Thomas Aquinas also had an insight that the idea of creation was compatible with a time that didn't have a beginning in the past. He thought it was compatible. Now, question to José Ignacio. Again, the whole question of causality that you mentioned before in quantum physics. The connection between time and causality. Is it conceivable from a scientific point of view, causality that is outside of time and not linked to time?
Great question. Okay. Bella domanda.
in pochi minuti.
In pochi minuti, yeah. Okay. So, yes, you can formulate causality without reference to time. So let me try to explain. In this corner of the universe, there is Alice. Alice. In this other part of the universe, there is Bob. Causality amounts to the fact that if they are very separated and they cannot communicate, whatever Alice does not affect the measurements of Bob. You see, this is causality. So it's about the fact that the measurements that we make cannot be anything. They must respect this fact. So only a set of probabilities are consistent with causality. There is no need for time, okay? So this is why recently, in the last 10 years, there are experiments to check to what extent there are any violation of causality. But all the experiments are negative, so we have never seen any violation. And to be more refined, it turns out that we see that the probabilities that we measure are consistent with quantum mechanics, but not with theories which go beyond quantum mechanics. So it seems that causality is well understood, but it remains a subject of research nowadays. Is that sufficient? Okay.
Grazie.
One last question to both of you. Up to now, we've talked about a lot about the scientific side. I'd like to ask a more personal question now with regard to the fact that time is this experience that we continue to have. As human beings, we experience time, and this doesn't necessarily coincide with that physical variable that we use in our research. Time is memory, it's expectation, it's waiting for something, it's attention to the present, as St. Augustine said. I'd like to ask both of you, please, what connection is there, in your view, between time as a variable of nature and this experience that we as human beings have? Are they the same thing, and to what extent are they connected?
It is, of course, the job of the scientist to take a daily experience and abstract from that to distill out the essential features necessary to explain the world around us. And scientists have done that with many aspects of experience, both our perception of space and our perception of time and our perception of matter. These things have all begun as human experiences and have been turned into the somewhat dry mathematical formulae that describe the objective world out there. And the question is, in going from our human perception of time to the T that appears in the equations that describe the world, have we lost something important? And I believe there is still a mystery here. I spoke in my presentation about the arrow of time, the fact that when you play a movie backwards, it clearly is peculiar, that there is a direction to physical processes in the universe. Many people confuse this arrow of time with the psychological impression we all have that time is flowing or passing. There are many metaphors, one of which is the river of time. Time is like a river that flows. Even Isaac Newton spoke of time that flows equably, I don't know how that translates, without relation to anything external. So Newton had this idea that time has a sort of internal movement. The problem is that nothing that we write down in our equations of physics captures that flow or movement of time. We often say in daily life that time passes. And we even have an impression that time passes at different rates in different circumstances. I believe it's true that Einstein once said that an hour spent talking to a pretty girl seemed very different from an hour spent in the dentist's chair. So the problem we are faced is to try to decide, is this flow, this impression we have of time flowing or moving, does it have its explanation in psychology, in neurology, what's going on in our brains, or does it have its explanation in physics? Have we left something out of our description of the physical universe that reflects this impression we have that time is flowing or moving? I think this is one of the great unsolved problems about the nature of time.
You go? Okay, so I fully agree. I mean, I agree with the relevance of the question, and I agree with Paul. You see, I've lived in my life in Europe. I've lived in North America. I'm living in Asia. And I visit Peru, I visit South America. And the concept of time, it's very different. Very different in Thailand from New York. Very different. Okay. So there is a big issue about human feelings over there. So let me say something. I think that the fact that our brain handles past and future, it's common to other animals. Huh? It's an advantage. It's an evolutionary advantage. So you see, you have to take a decision to run away from a lion. Okay, it's advantage to think of the future. It's advantage to remember the past. So I think this idea that we live together remembering the past and foreseeing the future is common to many species. What I think is really different is the fact that we have consciousness. This is the fact that we reflect on this fact. It's the fact that we question why this is so. So I think that the big mystery is why our brain does this thing. It gets inside and questions why he works the way he works and why feelings come about. So I think that physics has at present very little to say. We are simply in the beginning of understanding things. I do think that science must proceed. There are very interesting experiments in biology, in neurosciences, but I think that humans are at the very early stage of understanding this issue. We are babies. We don't understand. Okay?
Grazie, è così.
Thank you. It is indeed like that. Well, I think that this has been a very dense meeting, perhaps sometimes rather difficult and arduous to understand, but I hope that each one of you have had the possibility of gleaning something of the beauty of science. Because in science, what's beautiful is that you take nothing, and even the most obvious things, for granted. Even what appears obvious conceals the most profound truth or element, for example, that time flows in a direction, and then the usefulness that can come of this knowledge. José Ignacio made various and gave various examples, and we know of many ourselves, and also the fact that new questions always arise. We're just at the beginning. Questions which clearly are addressed to the scientific method itself, and we can try and set them up as methodology in science. And there are questions which try to, however, go outside the scientific method. And that's why in San Marino we need to dialogue with philosophers, with theologians, and with people whose point of view is different from a methodological point of view. That's important for science to move in this open direction. And therefore, I think that what has come out is the paradox of man. That's what we've seen in this meeting through this reality of time. Think, for example, how our human time, the time that we experience, the memory that we have, what we can imagine to be the future, the time of life. The time of life is brief, is short. There's a psalm that says the years are 780 for those who are stronger. And compared to the 14 billion or 13.8 billion years or whatever it is of cosmic time, it's nothing. And yet, one should think, well, what would happen and what would be of these 14 billion years were there not at least at one point or dot in time, time that is memory, time that is attention, time that is expectation, conscious time, in other words, self-consciousness, which is what José Ignacio concluded with now. And this paradox of the vastness of the cosmos, which Paul illustrated to us, and this experience that we have of our experience of the demand to have a significance and a meaning. And as Leopardi the poet would say, everything appears a little and close to man. So ephemeral is it, our small time span seems to fill the whole time of the universe in some way. Allow me to conclude with a couple of brief citations. One is of an astrophysicist, the first astrophysicist woman in the United States halfway through the 19th century, Maria Mitchell. And she says that small as it is, our reality compared to the infiniteness of the creation, short as our lives are compared to the cycles of time, we are so imbibed with the totality, in a total relationship with time, that the fall of a sparrow is felt right to the infinite of time, and the words that we cry out fill the whole space, and its tremor and vibration fills all of time. This small point in universal time introduces a sense, a meaning, and it is self-consciousness which induces this meaning. And I'd like to make an analogy which I thought of yesterday thinking of this meeting, an analogy. In other words, thinking of what happens in our life, in man's life, what would our time be? What would our human time be were it not punctuated by events that give it significance? That too would be an insignificant, empty, void time. What would humanity be, the whole of humanity be, and every person be, without an event able to fill with significance every moment of our lives? And I'd like to conclude with these verses of Eliot, which are known to us, which describes the instant at which significance comes into time in history, in which time of life has entered into the time of man, as the time of man has become entered into the time of nature. And Eliot says, a moment not outside time, but in time, in that which we call history, selecting and dissecting the world of time, a world in time and a moment in time, but not a moment of time, a moment in time, but time was created through that moment, because without meaning there is no time, and that moment of time gave significance. Thank you, and thank you all, and thank you especially to our two speakers.